Good morning, everyone. Let's talk today about important concepts of Chapter 1 and Lab 1, which is matter and measurement. In Chapter 1, you will study about matters. What is a matter? Anything that has mass and takes up space or takes up volume is known as matter. So, chemistry is the study of matter. Or, in other words, we can say that chemistry studies anything that we touch, feel, see, smell, or taste because they all are matter. There are main three states of matter: solids, liquids, and gas. Solid has a definite shape and definite volume, uh, and there are strong forces of attraction between the molecules, and that's why they are very close to each other and forms a regular three-dimensional structure. Liquids have definite volume but indefinite shape. They take the shape of the container. The particles of a liquid, they are close together but not as close as you see in the case of solids because they have weaker attractions between the particles as compared to the solids. A gas has no definite shape, no definite volume. Gases are compressible, and gases have the weakest force of attractions present compared to solids and liquids. The next topic is the classification of matter. So, matter can be pure substances or mixtures. So, when we are saying pure substances, what does that mean? That means your matter is composed of a single component with a constant composition. All elements and compounds are pure substances. So, for example, if you have an element aluminum, if you have a metal copper, aluminum is just made up of only one type of component, which is aluminum. There is nothing else in there. If you're talking about the copper, it is just copper, it's not copper mixed with something else. So, then what are compounds? When a few elements or when more than one element combine together in a fixed ratio that cannot be separated by any physical change, we call that as a compound. For example, water. Water is not a mixture of hydrogen and oxygen. Water is where hydrogen and oxygen are combining in the ratio of 2:1, and now water has its own properties. It's a single component, it's not the mixture, it's a single component with a constant composition. Can I break down water H2O into hydrogen and oxygen by a physical change? A physical change means you are heating it, you are boiling it, and then you are another one is like using a magnet. If you are separating them, that's a physical change. But we cannot separate hydrogen and oxygen. We cannot separate water into hydrogen and oxygen. So it's a compound. Similarly, sodium and chlorine, they combine in the ratio of 1:1 to make this compound sodium chloride, which is salt. Salt has its own properties. When you are eating salt, you're not eating sodium and chlorine, you're eating sodium chloride. It's a single component with a constant composition. So all elements and compounds are pure substances, and then comes the mixtures. And of course, as the name says, mixtures, they are not, they're composed of more than one component, and so they have basically not just a single component, more than one component, and its composition can vary depending on the sample. For example, if you have a beaker and you have water in it, and let's say you put a pinch of salt in it and the salt dissolves, then we call it as a salt solution. That's a mixture. That's a mixture of salt and water. That is not a pure substance. And how can I say that it's a mixture? Because in mixture, you can separate the components by a physical mean. I can heat and the water will vaporize. What will be left? Salt. And then I can condense water back. So I can separate salt from water. So that means it's a mixture. So if you look into this flow chart, so we're talking about matters, then you think about can it be separated by a physical process? If yes, then it's a mixture. If you cannot separate it, then it's a pure substance. The pure substance, now the pure substances can be elements or compounds. So if it can be broken down into simpler substances by a chemical reaction, then yes, it's a compound. If no, then it's an element. So let's start with, for example, copper metal here. Can it be separated by a physical process? No. So it's a pure substance. Can it be broken down into simpler substances? No. So it's an element. Take another example. Let's say oil and water, oil-water mixture. Can it be separated by a physical process? Yes, it's a mixture. If oil is lighter than water, then it will be on the surface of the water. Then you can pipette oil out and you can separate them. Another example, trail mix. Can it be separated? Yes, you can separate them. That means it is a mixture. Think about air. Can it be separated by a physical process? Yes. Air is a mixture of different gases. There are so many gases. You cannot see them separately. That does not mean it's an element or a compound. Nitrogen, oxygen present in the air helps with the burning. Nitrogen helps with the plants. Carbon dioxide, we are exhaling carbon dioxide. So these are all the mixture of gases. The only reason is you cannot see them separately. So if your mixture is uniform throughout, then you cannot see the components separately. You call that as a homogeneous mixture. For example, salt solution. Again, if in this beaker you have a pinch of salt, the salt dissolves, you cannot see salt and water separately, then it's a homogeneous mixture. What will be a heterogeneous mixture? For example, oil and water mixture, because you can see them separately. If you're mixing oil with water, there are two separate layers. The next topic is the measurement. Now, every measurement is composed of a number and a unit. Let's say you're checking your weight on a scale, and or you're checking your temperature. 37 temperature has no meaning unless you put a unit. degree Celsius, degree Fahrenheit, Kelvin. So the number, the measurement has no meaning unless you put a unit. The mass of a body is 40. Again, that has no meaning because is it kilogram? Is it gram? What is it? So your number is meaningless without the unit. So when we are putting the unit, then we have to understand that there are two different type of unit systems. The one is the metric system and the other one is the English system. So basically scientists, health professionals, and people in most other countries, other than America, they use the metric system. And what in the metric system, each type of measurement has a base unit, and all other units are related to the base unit by a prefix, and that prefix has a meaning. For example, in metric system, we measure length in meters, length, mass in grams, volume in liters. And then all these other units, they are basically related to this base unit just with 10 raised to the power something. For example, kilo means 1000. What that means? That means if I am talking about kilometer, I'm talking about 1 kilometer equals 1000 meters. So look at this diagram and it's going to be very useful for your exam. Let's say we are talking about, again, length, meters. You're given the length in meters and you have to, let's say your length is given in kilometers and you have to change it to meters. So this is your starting point because you already have kilometers. You are here. How will you go from kilo to meters? You're making 1, 2, 3 jumps in the forward direction. If you have one dot, look, I'm drawing one dot. One dot means multiply by 10. So what does that mean? That 1 kilometer equals to 1000 meters. 1 hectometer is equal to 1 hectometer equals to 100 meters. 1 decameter equals 10 meters. Now these units are larger than your base unit and these units are smaller than your base unit. Give me 1 second. What does that mean? That means, for example, let's think about deci. 1 decimeter equals to, now you're going backwards. That means 0.1 meter. Centimeter to meter. 1 centimeter equals, here 1, 2, 0.01 centimeter. Oh, sorry, meter. So if you're moving 2 places back, then look, you have 2 digits after the decimal. If you notice here, I'm putting one dot. One dot means multiply by 10. But here, this is milli, this is micro, and this is nano. If you're going from milli to micro, 3 dots means you're going to multiply by 1000. Micro to nano, you're going 3 dots, means you're multiplying it by 1000. Look at this problem here. How many grams of aspirin are in 325 milligram of tablet? The easy way to do these questions is you always write down the number that is given to you in the question, and then you draw a line and you put 1. Then whatever unit is written here, you put that down here so that you can cross it out. And you have to convert it into grams, so you put grams here. This is my grams is here and my milli is here. Out of these two, which one is bigger? More on the left side is bigger. So I'm going to put in front of the bigger one, I'm going to put 1. And then how many jumps I have to make to go from the bigger to the smaller one? 1, 2, 3. That means I am going to put 3 zeros here. So 1 gram is equal to 1000 milligram. Milligram cancels with milligram. 325 divided by 1000 is 0.325 grams. English system requires a conversion ratio to move between the measurements. There is no other way other than memorizing it. For example, length is measured in feet, inches, yard, miles, and if you have to go from feet to inches, foot to inches, you have to know this conversion factor. Mass can be measured in pounds or ounces. Volume can be measured in pins, quarts, cups. These are the English units, and in America we use the English system. There is nothing like multiply or divide by 10 to the power to go from one unit to another. Now all these numbers, class, they are exact numbers. They are not precisions, they are not approximate numbers. 1 feet equals to exact 12 inches. 1 yard is equal to exact 3 feet. It is very important to know whether they are exact or they are approximations. These are not our measurements. These are exact numbers. But if you look here, metric to English, for example, centimeter, that's a metric unit. Inch is an English system unit. And so if you're going from English to metric, metric to English, then those are not really considered as exact numbers. Those are considered as our measurements. They have to measure it, how much 1 inch will be equal to. These are measurements. And again, you will see in few minutes why we need to know that these relations, whether they are exact numbers or just the measurements. All these are measurements except the very first one, converting inch to 1 inch equal to 2.454 centimeter. That is considered as the exact one. Now look at this question. Convert 125 pounds to kilograms. So remember what I said before, that write down the number that is given to you in the question first, draw the line, put 1, and then you put the same unit down here, pounds, and then you have to convert it into the kilograms. And I'm given the relation here. My kilogram is going to go on the top. 1 kilogram equals 2.20 pounds. Pounds and pounds cancel out. Let me get my calculator. And 125 divided by 2.20 is, in the calculator it is showing up 56.81818. And I am going to put my answer as 56.818. 8 kilogram. Why just 3? Why did I just put 3 digits? What kind of rules decide that? Okay, let's do one more problem and then we're going to go back to those rules. I'm given the speed in the units of 60 miles per hour, and the question is to change this speed to kilometers per second. What that means is that I have to convert miles to kilometers, hours to seconds. So let's work on one unit at a time. First, I'm going to convert my miles to kilometers, and then the reason I put miles here in the denominator so that I can cross them out. So that means if hour is here in the denominator, that means I have to put here in numerator, and here will be my seconds. Now comes the conversion factors. So first thing, you all should know hours to seconds. 1 hour equals 3600 seconds. And this I can give you that 1 mile equals 1.609 kilometers. So hour cancel with hour, miles cancel with miles. What I'm left with, kilometers per second. So let's do the calculation. So what I'm doing in my calculator, I'm multiplying first all the it should be 60.0 miles. So I'm multiplying all the numbers given in the numerator. 60.0 times 1.609 times 1, and then dividing it by 3600. And I got, in my calculator, I got 0.02682 kilometer per second. And I am going to write down this answer as 0.0268 kilometer per second. So how will I decide how many digits I should be putting in the answer? That depends on the significant figure rules. So what are significant figure rules? For that, first you need to understand numbers. Numbers used in chemistry are either exact or inexact. Exact number means that you get it by counting the objects. For example, number of students sitting in the class, or we have 10 fingers, we have 10 toes. And then remember, in the metric system, 1 meter equals 100 centimeter. That's exact. Or 1 foot equals 12 inches. English to English, metric to metric. They are exact numbers. On the other hand, inexact numbers, they result from the measurements or observations and contain some uncertainty. For example, you're measuring the mass of the beaker, one measuring your balance is showing the mass as 10.5 grams, the other one is showing 10.54 grams, another one is showing 10.543 grams. So there is some sort of uncertainty. One 10.54, 10.543. So what we can see in these measurements, we are certain up to here, but then we have one extra digit that shows some uncertainty. So basically, significant figures are all digits in a number, including one estimated digit. We apply these significant figure rules only on measurements. We do not apply them on exact numbers. 1 feet equal 12 inches. How many significant figures are there? That has no meaning because that's not a measurement. So first let's look at some rules and then we'll see how we apply them on the measurements. All non-zero digits are significant. So how many non-zero numbers are here? 4. So this number has 4 significant figures. What about this one? 6. A 0 is significant only if it occurs between two non-zero digits. So look here, this 0 is between 2 and 4. Is that significant? Yes. Then how many significant figures are in this number? 3. Or 0 is significant if it is at the end of a number which is known as trailing 0, but then there should be a decimal in the number and that decimal can be anywhere. So this is a trailing 0. These two are trailing zeros. Are they significant? Yes, because both of these numbers have decimal. So how many significant figures are here? 4. How many are here? 4. A trailing 0, again the 0 at the end is not significant if there is no decimal in the number. This is a trailing 0, trailing 0, trailing 0, trailing 0. They are not significant because there is no decimal. So this number has 2 significant figures, 2 significant, 2 significant, 1 significant figure. Now how do you apply these significant figure rules when you are multiplying or dividing the numbers? So let's say the question is find the area of a rectangular box with length 10 centimeter and width 5.2 centimeter. These are my measurements. I measured it maybe using the ruler. So if they are my measurements and then I'm using my measurements in the calculation, area is length times width, 10.0 centimeter times 5.2 centimeter. Then if I am using my measurements and multiplying or dividing it, my answer should have the same number of significant figures as the original number with the fewest significant figures. What does that mean? How many significant these are my original numbers. How many significant figures are in 10.0? 3. How many are in 5.2? 2. And you go by the fewer. That means my answer needs to have 2 significant figures. So if I'm multiplying 10.0 with 5.2, my calculator is showing 52. So then 52, how many significant figures are in 52? 2. So my answer should be 52 centimeter square. If I'm writing this as 52.0 centimeter square, that will be wrong because then I'm putting 3 significant figures. So for example, here is a block and let's say you measured the mass of this block and the mass of this block is 40.53 grams, and then you measure the length, width, height, and let's say the volume of this block is 10.8 0 centimeter cube, and the question is to find the density. Density is mass by volume, which is 40.53 divided by 10. So if you're going to do it in the calculation, in the calculator, you will get 4.053 gram per centimeter cube. Is my answer should be reported like this? No. 40.53 has 4 sig figs, 10.0 has 3 sig figs, and you go by the fewer because we are dividing. So that means my answer should be 4.05. Now keep in mind, I have to stop here, then I'm going to look at the next number. If this number is less than 5, then you leave it like that. But let's say if the answer would have been 4.058, so the first number that I'm ignoring is 8. Since 8 is more than 5, that means you increment the last digit by 1. But in this case, we do not have to do that. So how do you apply the significant figure rules in addition and subtraction? Let's look at this question. Let's say the mass of the beaker is 10.1 grams, and then you added the salt in the beaker, and the mass of the beaker plus salt is 12.52 grams. The question is find the mass of the salt. So your mass of the beaker plus salt is 12.52 grams, and the mass of the beaker only is 10.1 grams. You have to find the mass of the salt. So it is, you just have to subtract these two numbers. Now in addition and subtraction, what do? You look at the number of digits after the decimal. Or let's say you look at the number of significant figures after the decimal. How many significant figures you see after the decimal here? 2. How many you see here? 1. And then you go by the fewer. That means your answer should have only 1 decimal place. So once I subtract it, 5 minus 1 is 4, 2.42 gram. If I will just leave it as 2.42 gram, that is an incorrect answer. So I need only 1 decimal place. So my answer, so what's the next number? 2. Since it's less than 5, I don't have to increment this number. So my answer will be 2.4 grams. Next topic is scientific notations. In science, sometimes we use very large or very small numbers. So to write numbers that contain many leading zeros or many trailing zeros, we use the method which we call it as the scientific notation. I should have said notation. In scientific notation, a number is written as y times 10 to the x, where this y is a number between 1 and 10, and this x here, this component x, the exponent, can be positive or negative. So for example, let's say you are given 2500, and the question is, these are numbers written in the standard form, and the question is write down in the scientific form. Now scientific form means your decimal has to be after the first non-zero number. That means your decimal has to be after 2. Where is decimal right now? If you cannot see it, it's here at the end. Where should it be? It should be after 2. It should be after the first non-zero number. So what we're going to do, you're moving the decimal to the left. How many places? 1, 2, 3. If you're moving decimal to the left, your x is positive. So I'm going to have 2.5 times 10 to the power, how many places you move backward? 3, 10 to the third. Now the number was 2500. How many significant figures are in this? 2. These zeros are not significant because there is no decimal. So that means when you're converting it into the scientific form, you should still have 2 sig figs. Similarly, let's look at this number 0.036, and you have to change it to the scientific form, and we want the decimal to be after first non-zero number, and my first non-zero number is here. So I have to move decimal 2 places to the right, and if you are moving decimal to the right, your x, the exponent part, is negative. So this will be 3.6 times 10 to the negative second, because we move 2 places to the right. 0.036 has 2 sig figs. Here also we have 2 sig figs. Density, as we discussed in one of the examples, density is the ratio of mass and volume. Mass and volume are extensive properties. Extensive properties means that depend on the mass. If you're going to have more mass, means it's going to be more volume. But the density is an intensive property independent of mass. So whether you take a small piece of copper metal or a big piece of copper metal, the density of copper will stay the same. A less dense substance floats on the top of a denser liquid. So let's look at this question. If a piece of rock has a volume of 0.73 liters and a mass of 1524 grams, what is the density of the rock in grams per milliliter? What is density? Density is mass by volume. The mass of the rock is 1524 grams and the volume is 0.73 liters. We want density in grams per milliliter. That means I have to change this liters to milliliters. I will put liters on the top so that I can cross it out, and milliliters on the bottom. And if you're going to go back to your original chart, you will see 1 liter is equal to 1000 milliliters. So now my answer will be in grams per milliliter. So what I have to do is I have to divide 1524 by 0.73, and then I also have to divide it by 1000. So the calculator shows 2.08767. These are my measurements. We measured the mass and the volume. That means in the answer I have to apply the significant figure rules. How many significant figures are here in 1524? There are 4 significant figures. How many are here in 0.73? Only 2. This 0 is not significant. 0 is significant only if it is in between 2 non-zero numbers or it is at the end with the decimal. Should I be looking at the significant figures in this 1000? No, because this is not my measurement. This is an exact number. We do not apply the significant figure rules on exact numbers. So 4 here, 2 here is a division problem. So you go by the fewer. That means your answer should have only 2 significant figures. So I will go with 2.0. But then what's the next number? 8, more than 5. So my answer will be 2.1 grams per milliliter. Another example. If the density of acetic acid is 1.05 grams per ml, what is the volume of 5 grams of acetic acid? I need the volume. Volume is in the milliliters. So I want to find out the volume of 5 grams of acetic acid. So I'm going to write down this first, 5 grams of acetic acid, draw a line, put 1. And then I have to put grams down here so that I can cross them out, and milliliters on the top. And what does that mean? 1.05 grams in 1 milliliter. So that means what I have to do, I have to divide 5.0 with 1.05. And again, it is showing 4.6190 grams, cancel, milliliter. These both are my measurements. This has 2 sig figs. This has 3 sig figs. So that means my answer should have fewer, means 2 sig figs. But is it going to be 4.7 or 4.8? 4.8. Why? Because the next number is, if the next number is 5 or more than 5, you increment the last digit by 1. Specific gravity. It is a quantity that compares the density of a substance with the density of water at the same temperature. So specific gravity is basically density of a substance divided by density of water, and the density of water is 1.00 grams per ml. So basically, I should say the specific gravity has no units. Why? Because we have grams per ml on the top and grams of ml on the bottom. So I can say the specific gravity is equal to the density of the substance but with no units. Accuracy and precision. Accuracy is a measure of how closely the results agree with the correct value, and precision is how much reproducible the results are. More the number of decimal places, more precise the data is. So let's say the mass of the block is 10.5 grams, 10.54 grams. So a student measured the mass of that block on different weighing machines, and the student reported 9.57, 9.58, 9.56, 9.55. Is that an accurate data? No, because it's not very close to the correct value. So it's not very accurate. But is it precise? Yes, it is precise because your each answer, your each value is close to each other. It's a precise data, but not an accurate data. The last topic here is the temperature. Temperature is a measure of how hot or cold an object is. 3 temperature scales are used: Fahrenheit, Celsius, and Kelvin. That Fahrenheit is the most common in the United States. Now, if you have to go from one unit to another, for example, to convert from Celsius, let's say the temperature is given in Celsius and you have to convert it into Fahrenheit, you use this relation. If it is given in Fahrenheit and you have to change it to Celsius, you use this one. And if you're given in Celsius and you have to change it in Kelvin, then you use this. These 1.8 and 32, these numbers are exact numbers. So that means when you're doing the calculations and you're reporting the answer, then you should not look at the significant figures in 1.8 and 32. For example, let's say a person had a temperature of 104 degree Fahrenheit. Then what is this temperature in degrees Celsius? So I'm given Fahrenheit here and I have to find degrees Celsius. So my degrees Celsius equal degree Fahrenheit, which is 104 minus 32 over 1.8. And when I'm going to solve it, I'm going to get 40 degree Celsius. How many significant figures I should have? It depends on this number. Because all other numbers are exact. 104 has 3 significant figures. So my answer should have 3. So I have to write down my answer like this: 40.0 degree Celsius. From here onwards is your lab, which you really have to submit. The first one is the measurement practice. It is record the measurements indicated below. So I have solved these two. You are going to solve these two here and you're going to submit it. And the way I'm writing it here, I need the exact, not the exact, you have to use this format. I need a sentence here with the measurement value. Again, I need a sentence here with the measurement value. So let's say this is a ruler and you have to write down what the measurement is. Let's say you're using this big block. This is my ruler and this is a block and I'm measuring the length of this block. So pick any 1, 2, 3, 4, pick any two numbers, for example 4 and 3 next to each other. 4 minus 3 is 1. And how many points do you see drawn in between? 10. That means this 1 is divided into 10 equal parts. That means this each part here is equal to 0.1. So that means if you are going up till here, so 1, 2, 3, 4, 5, 6, you are certain about 3.6. But remember, in measurement, you always put one estimated digit. So let me clear this and make it a little bit bigger. So again, look, 3.1, 2, 3, 4, 5, 6. I'm certain about 3.6. It is between 3.6 and 3.7. So I have to put an estimate at the second decimal place because I'm certain about the first decimal place, 0.6. So I'm writing 3.67 because I feel like it's a little bit more close to 3.7. So the point is, you're certain here 3.6, but you always put one extra digit. Let's look at the next example. Again, pick any two numbers. Let's say I'm picking 8 and 6. 8 minus 6 equals to 2. How many points are in between? 10. So your 2 is divided into 10 equal parts. That means each part is worth 0.2. So let's look here. So this is my 6 and this one is going to be 6.2, 6.4, 6.6, 6.8, 7, 7.2, 7.4. And I'm certain about 7.4. But then this is not exact as 7.4. It's between 7.4 and 7.6. So that means I have to put one estimated digit at the second decimal place. So give me 1 second. So I put 5, 7.45. So you're going to give your estimates. You're going to write down this whole line here, what you're picking the points, and then you're going to give the measurements. Your next will be the determination of a density of a regular shaped solid. In your LO1 packet, you will see you have a paper ruler. If you have it with you at home, fine. If not, then you can use that. And you're going to measure the length, width, and height of this block using that metric ruler. Keep in mind, you're measuring it on your screen. It's not in front of you. You're measuring it on the screen. So everyone is gonna, based on what your screen size is, this is gonna show up as a different length, width, and height. Anytime you're using the metric ruler, you put the length, width, and height. When you're using the metric ruler, you put up to 2 decimal places. And here I'm giving you one example. This is just an example so that you don't make mistakes here. And this is, let's say I measured it not for this block, something else, and I got my length, width, and height like this. I have to report up to 2 decimal places. If I'm just going to write down 2.5, that is wrong. You will end up losing 2 points. So length, width, and height up to 2 decimal places. And then you calculate volume. What is the volume? If the length, width, and height of the blocks are known, length times width times height. And I multiplied it. And since these are my measurements, so that means I'm applying the significant figure rules. There are 3 here, 3 here, 3 here. That means my final answer needs to have 3 significant figures. And that goes here. Now I'm providing you the mass of this block. Let's say it is 10.520. That means calculate the density. What is density? Density is mass by volume. Means this number by this number. So again, if you look at an example here I assume mass as this. So density is mass by volume. This is my mass. This is my volume. Mass has 5 significant figures. Volume has 3. And you go by lower number. So that means my final answer should have 3. So you have to do this using this block and using the paper ruler that is given to you in the packet. You're going to have your own data. I gave you an example here so that you do not make mistakes in putting the decimal places or the significant figures. So that's a kind of second data you have to report. The first one was the last, this one. Now you have this one. Then the next is, you're going to do this experiment, and you're also going to take the pictures of this experiment, and you're going to copy paste those pictures in this document, because I want to make sure you did the experiment. For this experiment, what do you need? You're going to look it in your packet, and you need the graduated cylinder, either 25 or 50 milliliter. And you also need there is a screw, and you have a weight of the screw written on the Ziploc bag. You need that. So first you're going to fill your graduated cylinder halfway through water, exact half. And you're going to record the volume of the water, and it says clearly record it to the 100th place. 100th place means you need to have 2 digits after the decimal. And again 2 digits after the decimal. And again, class, I'm giving you an example here. This is not the data for your, this is just an example. Look, I'm putting 2 decimal places. That goes here. You read the lower meniscus. So I'm here, if you look at this diagram, and here is the meniscus. So let me, so if I have to read here for this one, this is the line of 20. So if you look at these numbers, you're going to read this part black, not the top one. Now here, this is 20, This again, this big line is 21. This big line is 22, but this is not, has not reached there. So if I had to write down something for this, I am going to write down 21.50 for this. That's what I used in the example. You're not gonna have this, you're gonna have your own. And what you're going to do, you measure the initial volume, write down here, and then you slightly tilt the graduated cylinder and put your that metal sample, that the screw, that the nail that's in there, and then you read the level of the water again. Of course the level of water is going to rise, and that goes here. So what will be the volume of metal? Then how do you find out that? Final minus initial, that goes here. Mass of the metal sample is given to you on the Ziploc bag. You write down that here, and then you calculate density, which is mass by volume, and make sure you report the correct number of significant figures. Please read this. Once you found the density, then you match your number with the densities given here. Remember, you're not going to find the exact one. Pick the closest one. Let's say if I am getting, for example, I'm getting 1.244. So which one is the closest one to 1.244? It's aluminum 2.71. So I'm going to put that as an answer. Don't forget to take the pictures of these. I need to see definitely a picture of the nail, the screw inside the graduated cylinder. The last one here is the measurement activity. This is the fourth one, and here you're not doing any lab. You just, oh yes, you are doing the lab, I'm sorry. What you're going to do, you're going to take the 100 milliliter graduated cylinder, and you're going to put 9 milliliter of water in that using a pipette, barrel pipette. You can put straight some up to 8 milliliter or something, and use the rest drop by drop to make it 9 milliliter of water. And then you're going to transfer that 9 milliliter of water into a 10 milliliter graduated cylinder, and you're going to measure the volume. So what exactly you are doing? Again, you're taking a 100 milliliter graduated cylinder, you're going to put 9 milliliter of water in it. It's hard to put exact 9 milliliter. Put 6 or 7, and then use the dropper to put the rest. When it touches 9 milliliter, you then stop. And then using this graduated, take the small 10 milliliter graduated cylinder and transfer this water to this 10 milliliter graduated cylinder, and then read it here. Read the level of the water, read the lower meniscus, 2 decimal places, and then you're going to write down here. That will be your measured volume. And again, this is my example. So let's say I took 9 milliliter of water, I transferred it to 10 milliliter graduated cylinder, and if I'm reading it here, I'm always reading it here. And let's say I'm reading it as 9.50. Get rid of the water, do the second trial. Again, take 9 milliliter of water in the 100 milliliter cylinder, transfer it to the 10 milliliter graduated cylinder, read the volume, put here. Trial 3, put here. Then you're going to calculate the average. What will be the average? Average of these 3 numbers. That will go here. This is just an example. Then you're going to calculate the deviation. How do you calculate the deviation? Deviation is your measured value, which is here, minus the average. So if you look here, and this is an absolute value. So absolute means whether your answer is negative or positive, the final will be positive. So this is my measured value, 9.50 minus average. 9.50 minus 9.27 is 0.23, and the absolute of 0.23 is 0.23. So you're going to do these trials. So look here, 8.86 minus 9.27. This is a negative number, but since it's the absolute, it's going to be positive. and then you take the average of these deviations and that go here. So you definitely have to take the pictures of part B and C because you're really actually doing the experiment. You're going to transfer the picture to your computers. You're going to copy paste the picture into this document under this page. Then you're going to save your Word document with this L1 Lab 1 matter and measurement, your first name, last name, and date, and then you're going to upload it under this lab report. And I'm going to show you in a minute on Canvas. It's not the exact this name. I'm going to show you on the on Canvas.